unfold.
For as long as we've been telling stories, there has always been this one, this one absolute truth. We all die.
Right. It was the great equalizer. It didn't matter if you were a king or a farmer.
Exactly. You can go all the way back to the Epic of Gilgamesh, literally the oldest story we have. And it's all about this hero realizing that eternal life is, well, it's just not on the table for humans.
And we built everything around that idea. Our philosophies, our religions, they're all, in a way, coping mechanisms for our own mortality.
But something has fundamentally changed. In just the last couple of decades, that ancient certainty has been challenged not by a philosopher, but by the molecular biology lab.
It's a profound schism. The whole narrative is shifting.
Okay, so let's dig into that schism because it's a huge deal. The new argument, the one gaining traction in labs all over the world, is that aging isn't some mystical fate.
No, it's a technical problem.
Just a technical problem. A collection of measurable biological errors, information loss, things that can be, in theory, engineered.
It's the ultimate engineering mindset. You see it with figures like Dr. Aubrey de Grey, who broke aging down into 7 types of damage to be repaired.
Or Dr. David Sinclair, who really frames it as an information problem.
Exactly. For them, the question isn't if we can solve aging, but when and how.
And the science that's coming out of this new mindset is it's breathtaking. We've mapped the mechanisms of decay. We have the blueprints.
Which leads to these almost unbelievable projections like longevity, escape velocity, LEV.
LEV. Let's define that because it's a critical concept. This is the point where for every single year you manage to stay alive.
Science adds more than a year to your life expectancy. The progress curve overtakes the decay curve.
And futurists like Ray Kurzweil are predicting this could happen as soon as 2029.
That's just around the corner.
It's astonishingly close. And if he's right, that means the first people who will never die of old age, they're probably alive right now, maybe in their 30s or 40s.
That's the scientific awe right there, the peak of it.
But, and this is the core of our deep dive today, for every bit of that awe, there's an equal and opposite warning, isn't there? A warning about what this does to society.
A profound warning. Because if we achieve this immortality, where aging is optional, what kind of world does that create?
The first fear, and it's a big one, is the commodification of life itself. We're already seeing billionaires pour fortunes into this, reprogramming their own biology.
And that doesn't just create wealth inequality, it creates biological castes, where the rich don't just have more, they fundamentally are more. They're better, longer-lasting machines.
And then there's the psychological trap. Yuval Noah Harari talks about this idea of immortality.
Right, you can still get hit by a bus.
Right, but if you don't, you keep going. And Harari warns this leads to a cushioned cage, a state of extreme paranoia.
If you have centuries, maybe millennia to lose, your aversion to risk becomes absolute. You stop living, really. You become experientially dead just to stay biologically alive.
And that tension between the incredible scientific promise and this dystopian societal fracture, that's what we're exploring today. So let's start with the enemy. What exactly is aging? For so long, we could only describe the symptoms.
Right. Gerontology was a descriptive science. Now it's mechanistic. We're looking at the causes. And the framework for that is the hallmarks of aging.
It started with 9 hallmarks back in 2013, and now it's been updated to 12.
And that expansion is so important. It shows how much more we understand about the interconnectedness of it all.
We need to be really clear here. These aren't just symptoms like gray hair. These are the verifiable causes.
Verifiable is the key word. To be a hallmark, it has to meet 3 criteria. It has to show up during normal aging.
Oh.
If you make it worse in a lab animal, it has to speed up aging.
Makes sense.
And the most important one, if you fix it, if you therapeutically target it, it has to slow down or even reverse the aging process.
And that last point is the proof. It confirms the whole engineering hypothesis. All right, let's start at the absolute base layer, the information code. The first hallmark is genomic instability.
Our DNA, our core blueprint, is just under constant assault. UV radiation from the sun, Chemicals in our food, oxidative stress from our own metabolism.
I've heard it's something like tens of thousands of hits to our DNA every single day.
It's an incredible number, and for a while, our DNA repair systems are amazing. They're like little molecular mechanics patrolling the genome, but over time, they get tired, they get inefficient.
And the damage starts to stick.
Exactly. You get point mutations, which are like typos in the code. You get deletions, where whole sentences are ripped out, and you can even get, total chromosomal chaos.
So it's not just minor errors, it's structural degradation.
It is. You end up with this mosaic of dysfunctional cells all over your body. The operating system itself is degrading from physical damage. It's hard-coded obsolescence.
Next up is maybe the most famous one, telomere attrition. This is our molecular clock.
Right. So your chromosomes have these little protective caps on the end called telomeres. Think of them like the plastic tips on your shoelaces, the aglets.
They stop the important code from unraveling when the cell copies its DNA.
Precisely. But here's the catch. Every time a cell divides, those telomeres get a tiny bit shorter.
Until they hit a critical point.
At which point the cell panics. It sees its own code is now exposed and vulnerable, and it does one of two things. It either enters senescence, which is like a permanent retirement.
Or it triggers apoptosis, programmed cell death.
Which is why our tissues have a limited number of times they can replicate. It's a huge driver of why our immune system, for example, weakens as we get older.
Now, we do have a tool for this, right? The enzyme telomerase. It can rebuild the caps. So why don't we just switch it on everywhere?
And there's the first great paradox of this whole field.
Cancer.
Cancer.
Yeah.
Unrestricted immortal cell division is the definition of a tumor. The body keeps telomerase switched off in most of our cells as a critical safety brake.
So if we just flip that switch on globally,
we would almost certainly induce aggressive cancers all over the body. The engineering challenge isn't finding the gas pedal. It's designing a braking system that's smart enough to know when and where to apply it. We're not there yet.
Okay, that brings us to the third information hallmark. Epigenetic alterations. This is where David Sinclair's theory really comes into focus. Let's use that hardware-software analogy.
It's the best one. If your DNA sequence is the hardware.
The physical disk.
Right. The epigenome is the software. It's a layer of chemical tags on top of the DNA that tells the cell which genes to read, when to read them, and how loudly. It's why a skin cell and a brain cell are different, even though they have the exact same hardware.
And with aging, that software gets corrupted.
We call it epigenetic drift. The precision is lost. The system gets noisy. Genes that should be off get turned on, and vice versa. The cell starts to lose its identity. It's a skin cell that starts, vaguely expressing genes for a kidney cell.
Which is chaos. But the incredible implication here is that unlike a mutation, which is permanent hardware damage,
this is a software glitch.
And software can be rebooted.
It can be debugged. This is the source of so much optimism. The idea is that the youthful instructions aren't actually gone. They're just buried under all this noise. We just need to find a way to restore the factory settings.
Okay, let's shift from the code to the factory floor itself, the cell's maintenance systems. A young cell is clean and efficient. An old cell is.
It's a hoarder's house.
Yeah.
It's overwhelmed with junk. And that starts with the loss of proteostasis.
Proteostasis, that's the quality control system for proteins, right?
Exactly. Proteins are the little machines that do everything in the cell, but they have to be folded into very specific 3D shapes to work. Proteostasis is the network that ensures that happens correctly.
So what happens when that system breaks down?
Misfolded proteins start to accumulate. They're sticky. They clump together into these toxic aggregates. This is what we see in Alzheimer's disease, for example. The beta amyloid plaques and tau tangles, that's a catastrophic failure of proteostasis.
The cell literally becomes a graveyard of broken machinery.
It physically clogs up the works.
And that leads right into the next hallmark, one that got a major promotion in the 2024 update. Disabled macrotophagy.
Autophagy literally means self-eating. It's the cell's garbage disposal and recycling program.
So when a protein gets misfolded or a mitochondrion gets damaged, the cell is supposed to eat it?
It engulfs it, breaks it down into its basic components, and reuses the parts. It's the essential spring cleaning that keeps the cell running smoothly.
But in aging, that system just stops working as well.
It slows way down, the trash starts piling up, damaged mitochondria, those protein clumps, this stuff called lipofuscin or age pigment, the cell literally begins to choke on its own waste.
And this is one of the most exciting areas for intervention because we know how to turn autophagy back on.
We do. Things like caloric restriction or fasting or powerful activators, or drugs like rapamycin. They essentially trick the cell into thinking it's starving, which flips the switch from growth to clean up and survive.
And it works. This is one of the most proven ways to extend lifespan in lab animals.
Absolutely. Clear the trash and the system runs longer.
All right, category 3, the power grid, the cell's energy systems. Let's talk about deregulated nutrient sensing.
This is all about how your cells decide whether to be in growth mode or repair mode. You have two key sensors, mTOR and AMPK.
The yin and yang of metabolism.
A perfect analogy. mTOR senses abundance, plenty of food, and it pushes the cell to grow and divide. Anabolic. AMPK senses scarcity and pushes the cell to conserve, repair, and recycle. Catabolic.
And in aging, mTOR gets stuck in the on position.
It becomes hyperactive. The cell is constantly trying to grow, even when it's damaged and needs to repair. And this is critical. When mTOR is on, it actively blocks autophagy.
So the growth signal shuts down the cleanup crew.
Exactly. And that explains the paradox of why caloric restriction is so effective. By eating less, you suppress mTOR, which allows AMPK and autophagy to come online and do their repair work.
It's a trade-off, growth versus longevity.
Which brings us to the power plants themselves, the mitochondria.
Mitochondrial dysfunction. They make our energy, but they also create pollution.
They're the engines of the cell, making almost all of our energy currency, ATP. But that process, cellular respiration, is messy. It creates these toxic byproducts called reactive oxygen species, ROS.
Free radicals.
Right. They're like the smog from the power plant, and they damage everything they touch, DNA, proteins, lipids.
And as we age, the engines get old. They become less efficient.
Precisely. So they produce less energy, meaning you have less fuel to run on, and at the same time, they produce more pollution, more ROS.
That sounds like a death spiral.
It is a vicious cycle, and to make it worse, the specific process for cleaning up damaged mitochondria, called mitophagy, also fails. So you have these broken, polluting engines that you can't even remove from the system. The city is running out of power and choking on smog.
Okay, let's move up to the systemic level. The problems that affect the whole organism, and we have to start with cellular senescence. The zombie cells.
That is the perfect name for them. These are cells that have taken so much damage they've had to stop dividing, but they don't die. They just hang around.
They're not just passive, though. They're malicious.
They are actively toxic. They secrete this inflammatory cocktail of molecules called the SASP, the senescence-associated secretory phenotype.
And this SASP spreads to neighboring cells.
It's like a contagion of dysfunction. It pollutes the local tissue environment, driving chronic inflammation and corrupting healthy cells. It's a major cause of so many age-related diseases.
Which is why there's this huge gold rush around senolytics.
Senolytics are drugs designed to selectively hunt down and kill these zombie cells. Things like dasatinib plus quercetin. The idea is simple. If you can clear out the source of the toxicity,
the whole system can start to recover.
And this system-wide failure also means we lose our ability to heal. That's stem cell exhaustion.
Our regenerative reserves.
These are the master cells that are supposed to replace damaged tissues, but over time they get damaged too. They become senescent themselves, or they just lose the ability to differentiate properly.
And you see the results everywhere. Gray hair is a great example.
It's a failure of the melanocyte stem cells in your hair follicles. Weakness and poor healing is a failure of muscle stem cells. And crucially, the decline of our hematopoietic stem cells in the bone marrow is why our immune system gets so weak. The well is running dry.
With all this damage and all these zombie cells, the body's communication systems must just break down. Altered intercellular communication.
The signals get crossed. The whole system is full of noise, hormones, neurotransmitters, immune signals. It's all disrupted by this background of toxicity.
And this leads us to the two newest hallmarks, which were promoted to their own category in 2024. The first one is chronic inflammation. You called it inflammaging.
Yes, and its promotion to a standalone hallmark is so important. This isn't the good acute inflammation you get when you cut your finger. This is a low-grade, sterile, smoldering fire that never goes out.
Fueled by the zombie cells and all the cellular debris.
Relentlessly. And this smoldering fire is now seen as the foundation for almost every major disease of aging. Heart disease, arthritis, Alzheimer's. They all have chronic inflammation at their core.
And the final, newest hallmark connects all this internal decay to our environment. Dysbiosis, the gut-brain axis.
This one is fascinating because it links everything together. Our gut is home to trillions of bacteria, our microbiome. As we age, the balance of that community shifts. The good, symbiotic bacteria decline, and more inflammatory, pathogenic ones take over.
And this imbalance, this dysbiosis, has a critical effect. It causes leaky gut.
That's right. The barrier that lines our gut starts to weaken. And when that happens, bacterial fragments, like something called LPS, leak out of the gut and into our bloodstream.
And the immune system sees these fragments and goes on high alert.
It sees them as an invasion, and that drives that systemic chronic inflammation we were just talking about. It's a direct pathway from your diet and your gut health to the aging of your brain and your heart. It proves you can't look at aging in just one organ. It's a total system failure.
Okay, so that tour of the 12 hallmarks, it's daunting. It feels like this impossibly complex machine falling apart in dozens of ways at once.
It does. It feels like a hardware problem.
But let's get back to David Sinclair's information theory. This is the radical optimism. The idea that this isn't about hardware failure at all, it's software corruption.
The scratch CD metaphor is still the best way to understand it. The music on the CD, your actual DNA sequence, is mostly fine. There might be a few typos, but the song is intact.
The problem is the CD is covered in scratches, and the laser reader, the Epigenetic, can't read it properly anymore. It skips, it stutters, it plays the wrong track.
So aging isn't the loss of the information itself. It's the loss of the ability to read the information.
Which means the backup copy of youth is still in the cell.
It's still there. We don't have to fix every single piece of broken hardware. We just need to find a way to polish the CD.
And the tool that might let us do that comes from Shinya Yamanaka's Nobel Prize-winning work, the Yamanaka factors.
In 2006, Yamanaka discovered this cocktail of 4 transcription factors, OCT4, SOX2, KLF4, and 𝐏𝐿, or OSKM for short, that could do something incredible.
They could take any adult cell, say a skin cell, and completely wipe its epigenetic slate clean.
It resets it all the way back to a pluripotent stem cell, an embryonic-like state. It's the ultimate biological reset button.
But just like with telomerase, a full reset in a living organism is catastrophic.
It's lethal. If you do that to a mouse, you don't get a young mouse. You get a mouse full of tumors called teratomas as all its tissues dissolve into this undifferentiated slurry.
So the breakthrough wasn't just finding the reset button. It was figuring out how to not push it all the way down.
It was the discovery of partial reprogramming. The key is the dose. You pulse the factors, you turn them on just long enough to erase the epigenetic noise, the scratches, but not so long that you erase the cell's identity.
You polish the CD without wiping the song.
Exactly. And the landmark study that proved this could work in a living animal was incredible.
The one with the blind mice.
Sinclair's lab took mice with crushed optic nerves, a permanent injury. They engineered them so they could turn on 3 of the factors, OSK, with a simple antibiotic.
They left out 𝐏𝐿. Why was that one so important to omit?
𝐏𝐿 is a powerful oncogene. It drives cell growth like crazy. By taking it out, they dramatically lowered the risk of cancer while keeping the core reprogramming function.
And the result?
When they pulsed the OSK factors, they saw the epigenetic patterns in the nerve cells reset to a youthful state. The damaged nerves regenerated. And the mice could see again. That's not repair. That's a true age reversal at the information level.
And that single experiment, showing this was actually possible, has triggered an absolute gold rush.
An unprecedented one.
Right.
Which brings us to companies like Altos Labs.
The scale here is just hard to comprehend. They launched with $3 billion in funding.
$3 billion. That's not a normal biotech startup. That's a moonshot project. It's reportedly backed by people like Jeff Bezos and Yuri Milner, and they hired a super team, all the giants in the field. Yamanaka himself is on board.
This is the industrialization of immortality. It's taking this fundamental science and pouring massive capital into it to compress decades of research into just a few years.
The bet is simple. If aging is an information problem, the first company to safely crack partial reprogramming in humans has found the fountain of youth.
But the critics, like Charles Brenner, they raise a huge red flag here. The risk.
A massive red flag. They argue that resetting trillions of cells in a complex human body is exponentially more difficult and dangerous than doing it in a petri dish or a mouse's optic nerve.
The risk of inducing cancer, of losing control,
Yeah,
it's immense.
it is. Which leads to this strange dystopian possibility that the first people to receive this technology, the super rich, could also be the first people to suffer its catastrophic bugs, a very expensive, very strange way to die.
So while some are trying to reboot the software, others are taking a totally different path. They're trying to hyper-optimize the existing hardware.
Which brings us to the very strange world of the quantified self and its poster child, Brian Johnson and Project Blueprint.
Johnson is the ultimate case study. His stated goal is immortality, and he's treating his body like a platform to be engineered, outsourcing all his decisions to an algorithm.
The level of precision is just Extreme. He wakes up without an alarm. His sleep is that optimized. The first thing he does is measure everything, like his inner ear temperature.
Why that? What does inner ear temperature tell you?
He consistently runs cool, around 94 degrees Fahrenheit. A lower core body temperature is a classic biomarker of metabolic efficiency. It's seen in animals on caloric restriction. It suggests his body isn't wasting energy, it's running slow and cool, which correlates with longevity.
And then comes the food, this green giant sludge.
All right. It's not a meal, it's a nutritional delivery system. Every ingredient, spermidine for autophagy, cocoa-flavanols for blood vessels, is in there for a data-driven reason. Then it's a strict 60 to 90-minute workout, also optimized by data.
And then there's the pill regimen, over 100 pills a day.
It's a pharmacological assault on the hallmarks. He's taking metformin to control his blood sugar, mimicking fasting. He's taking NAD plus boosters like NMN to help with DNA repair. It's all tuned daily based on his blood work.
But we have to point out, it's not without risk. He was taking rapamycin, a powerful autophagy booster, but had to stop.
He did. He had side effects issues with his lipid profile, risk of infection. It shows that even with unlimited money and data, you're still experimenting on yourself.
And nothing captures the sheer strangeness of this pursuit better than his penis rejuvenation therapy.
It's a vivid example, for sure, but it perfectly illustrates the philosophy of reducing everything to a measurable data point.
So what's the therapy?
It's focused shockwave therapy. Acoustic waves that create microtrauma to stimulate the growth of new blood vessels. For him, erectile function is just another biomarker for his overall cardiovascular health.
But it's the measurement that's so telling. He uses a device, the Atom sensor.
Yes, to track his nocturnal erections. The goal isn't pleasure or intimacy. The goal is to achieve the quantifiable erection profile of an 18-year-old, which is about 3.5 hours of rigidity a night.
It strips all the humanity out of it, becomes another score to optimize on a spreadsheet.
And that's the warning. In the quest for biological perfection, you can algorithmically edit out the very things that make life worth living.
Okay, moving from optimizing the self to, well, borrowing from others, let's talk about blood and plasma. This all started with a pretty grotesque practice called parabiosis.
Living beside. It's where scientists would surgically fuse the circulatory systems of two mice, one old and one young, so they shared a blood supply.
And the results were disturbing, but undeniable.
The old mouse got younger. Its muscles healed better, it grew new brain cells, but the young mouse got older faster.
So it wasn't just that the old mouse was missing youth factors, it was that its blood was full of pro-aging factors.
Exactly, which led to this brief, very controversial market for young plasma exchange, YPE.
The vampire model. Companies like Ambrosia were selling plasma from teenagers to wealthy older clients for thousands of dollars a liter.
It was a PR nightmare, and in 2019, the FDA stepped in and issued a strong warning against it, citing no proven benefits and real risks.
But the science didn't stop. It just got smarter. It shifted from adding youth to removing age.
And that's the move to therapeutic plasma exchange, or TPE.
So it's not about consuming youth, it's about cleansing decay. How does TPE work?
It's basically like dialysis. They take out your blood, spin out the plasma, which is where all the toxic SAC factors and inflammatory junk from the hallmarks are floating around, and they discard it. Then they replace it with saline and a protein called albumin.
And the Buck Institute trial in 2025 showed this actually works.
It did. They found that TPE, especially when combined with an immune therapy called IEE, reduced biological age by an average of 2.6 years.
Just by filtering the blood.
Just by cleaning out the toxic environment. It's a pure engineering solution.
This entire quest inevitably pushes us beyond normal biology and forces us to ask what it even means to be human.
And you get into some really extreme ideas, like Dr. Sergio Canavero's proposed head transplant.
The Gemini Protocol. The ultimate expression of the idea that the self is just the information in the brain and the body is disposable hardware.
Right. But the engineering challenge is almost insurmountable, fusing the spinal cord.
How did he even propose to do that?
The plan was to use an ultra-sharp diamond nanoblade to get a clean cut, and then use a chemical glue, a fusogen called polyethylene glycol, to try and get the nerve endings to fuse back together.
Which the entire scientific community agrees is basically impossible right now.
Completely. The Russian volunteer, Valery Spiridonov, eventually backed out, but the fact that it was even seriously considered shows how desperate the desire to escape a decaying body can be.
Then we have something that's much closer to reality. Ectogenesis. The artificial womb.
Yes. Devices like the biobag have already been used successfully on premature lambs, keeping them alive and developing for weeks outside the mother. Human trials for extremely premature infants are on the horizon.
But the long-term trajectory is full ectogenesis, growing a baby entirely outside a human body.
Which on one hand could be a huge liberation for women, removing the biological risks and costs of pregnancy. But the dystopian warning is right there. The commodification of creation itself.
Turning birth into a sterilized, optimized manufacturing process.
Precisely.
And for those who feel they might miss this technological wave, there's the final gamble, cryonics.
The ambulance to the future. The idea is to preserve a legally dead person at liquid nitrogen temperatures, -196 Celsius, in the hopes that a future civilization can revive them.
But you have to be clear, it's not freezing.
No, freezing would destroy the cells. Ice crystals are like tiny knives. The process is called vitrification. They replace your blood with cryoprotectant chemicals that turn your body into a glass-like solid, preventing ice from forming.
It's replacing biological death with a kind of technological stasis.
And some people take the bet even further. They only preserve the head.
Neuroseparation.
Betting that the future will be able to clone them a new body or build a synthetic one and just attach the brain. It's the ultimate act of faith in future technology.
Before we get to the philosophy, there's one last really clever strategy we have to talk about. The veterinary vanguard.
The Trojan horse.
Using our pets, specifically dogs, to push longevity science forward. How does that work?
It's a brilliant move by companies like Loyal. Getting a human longevity drug approved is nearly impossible because the FDA wants you to treat a disease, and aging itself isn't classified as one.
But dogs offer a perfect test case, especially large dogs.
Right. Great Danes, for example, die much younger than Chihuahuas. The theory is that high levels of a growth factor, IGF-1, that makes them grow big fast, also makes them age fast.
So Loyal developed a drug, LOY001, to lower those IGF-1 levels.
Yes. But the truly historic part isn't the drug itself, it's what the FDA did in late 2023.
They accepted reasonable expectation of effectiveness for it.
Which was a landmark decision. It was the first time a major regulator accepted lifespan extension as a valid drug endpoint. Not treating arthritis in an old dog, but extending the dog's life.
So they paved the regulatory road.
They paved the entire road. Once aging is a treatable condition in one mammal, the argument to make it a treatable condition in humans becomes infinitely stronger. We are, quite literally, testing our own immortality on our pets.
Okay, so this brings us to the core of it all. The Prometheus paradox. We have this fire, this incredible technology. But if we can live forever, should we?
And the first casualty could be equality itself. Francis Fukuyama called transhumanism the world's most dangerous idea.
Why so dangerous? What's at stake?
He argues that the entire foundation of liberal democracy rests on one simple idea. That all humans share a common nature. We're all flawed. We're all mortal. That's what allows us to have a concept of universal rights.
But if the rich can buy themselves a different biology, a better one, that shatters.
It shatters completely. You create a biological caste system that is insurmountable. It's not about having more money anymore. It's about being a better machine. How can a normal human compete with someone who has centuries of life and enhanced cognition?
The philosophical basis for equality just evaporates.
And then there's the personal psychological cost. Let's go back to Harari's cushioned cage.
The trap of immortality.
If you knew you had 500 years of healthy life ahead of you, what would you do? Would you go skydiving? Would you travel to a dangerous country? Would you even cross the street without looking 5 times?
Probably not. The fear of losing all that potential time would be paralyzing.
That's his warning, that the very quest for infinite life could lead to the end of a life fully lived. You become so risk-averse that you retreat into a perfectly safe, sterile, and boring existence. Biologically alive, but experientially dead.
Trapped by the fear of loss.
Ew.
But we have to give the other side its due. The transhumanist argument from people like Peter Thiel.
Who are funding a lot of this research.
Right. And their view is that accepting death isn't wisdom. They call it Stockholm Syndrome.
It's a coping mechanism we developed because for all of human history, we were helpless against it. Now we're not.
Their argument is that aging is just a disease that encompasses all the others: cancer, heart disease, dementia. We fight all of those, so why should we give the umbrella condition a free pass?
For them, it is a moral failing not to intervene. To have the tools to end the suffering of old age and to choose not to use them is, in their view, the real ethical crime.
And this whole debate, the science, the ethics, the risk, it all comes to a head with that prediction we started with. longevity, escape velocity.
Kurzweil's 2029 date. Even if he's off by a decade or two, it makes the whole conversation incredibly urgent.
It's not an abstract future anymore.
No, it means our generation is the bridge. We are the first people who might actually make it long enough for science to get us over the finish line.
And therefore, the last people who might die of old age in the way humans always have. The choice is becoming very, very real.
So as we wrap up this deep dive, I think the conclusion is pretty clear. The science is real. The end of aging is no longer a question of if. It is strictly a question of when, and crucially, for whom.
The code has been cracked. We have OSK factors for rebooting cells, senolytics to clear out zombie cells, TPE to cleanse the blood. We've moved from theory to engineering.
But the risk of societal fracture is just as real. The money pouring into Altos Labs, the extreme optimization of Project Blueprint, it all points to life becoming the ultimate luxury good.
And that could create a world with a level of inequality we can barely even imagine. Those biological castes.
And in our personal quest to optimize every metric, to measure every bodily function, to sterilize every risk, we do have to ask what gets lost.
Are we editing out the very fragility and finitude that gives life its meaning, its urgency?
Our story now is the story of Prometheus. We have this incredible fire, this science that can save us from so much suffering. But that same fire could burn down the entire structure of our society. The weight of that choice is on us, now.
So here's a final thought for you to take away. If you learn tomorrow, with absolute certainty, that you would not die from aging, what is the one spontaneous, risky, unoptimized thing you do today that you would immediately stop doing simply because you now have far too much to lose?